or welcome to lesson 5. So we're going to understand and apply the second derivative test to identify concavity, points of inflection, and the relative extrema of a function. So notice we've just discussed the first derivative test, which involves us taking the derivative of a function and using the information the derivative gives us to identify the relative extrema by looking at where the function is increasing and then decreasing and using the information we can glean from that. This second derivative test, as you might guess, deals with taking a second derivative. So let's go ahead and jump in. Here is the function x cubed. What you should do is copy down this graph and all the green and red points that I have there. You don't necessarily need to copy down each of these questions. You just want to write down the answers. In other words, what you're observing about the graph to sort of help concretely display your thoughts so that you can more easily understand the concept. Go through and answer A through F, and then we'll work through this a little bit together to discover the meaning of the second derivative. All right, so as you can see, I've started drawing the tangents to the curve at each of these points. So here's the one that goes through the first point, one that goes through the second point. You can imagine the one that goes through the third point, the one that goes through the fourth point. I'll go ahead and complete these now, but you should be noticing what's happening to the slope of each of these tangent lines. So if I take a look at the tangent lines at each of these points along my function, what I will notice is that the tangents are getting steeper and steeper. And of course, the slope of the tangent is the same as the slope of the function at that point at which they intersect. And so what I notice is that as I am moving from 0 towards positive infinity, the slope at each point is increasing. So what I can say is a couple of things. The first is that the slope of my function f is increasing. And what that means is that my derivative, f prime, which represents the slope of the function, f, is also going to be increasing as I move from 0 towards positive infinity. And this is interesting to think about because the derivative itself is a function, which means that the derivative itself has some sort of rate of change, right? The slope is changing as we move from left to right. How would we describe the shape of my function f from 0 to infinity? And there are a couple ways that you can do this. So looking at the function, you might say, oh, it's opening upwards. That's correct. You could also say that it looks kind of like a bowl shape, an open bowl shape. And yes, that's also an accurate way of describing it. The mathematical term here is concave. Now the word concave means to curve inward. And so we can see that this is curving inward, and we say that it's concave up because it's curving inward, and so the part that is curving inward is facing up. Okay, so we say that it is concave up. All right, now let's go ahead and repeat these, what we did here for the right side of my function with the left side. So here I've drawn all the tangents to the points in red. Now, what do I notice is going on or is happening to the slope of the function f? Well, what I'm noticing here is that as I move from left to right, I can look at the slope of the tangents to visualize what the slope at each point of my function will be. And I notice that they get shallower and shallower as I move towards the right or closer to 0. And so I can see that the slope is decreasing. This, of course, means that my derivative, f prime, as I move closer to 0, is going to be getting smaller and smaller. Now, notice, these values are all positive slopes, right? Just like here, my function was increasing, but the way in which it was increasing was getting bigger itself, right? The slope was increasing. Here, even though the slope is still positive, the slope is decreasing, which means, again, that my derivative is going to be decreasing, in that the derivative itself has a rate of change, a rate at which itself is changing. So how can I describe the shape of f from negative infinity to 0? So here I'm thinking about this part of the graph. Again, here I can think about it being concave, except here the concavity is pointing downwards. And so we call this concave down. And what we can notice about these two situations, where we have something that's concave up and something that's concave down, is the certain situation which created something to look concave up or concave down. Concave down was created by the slope decreasing. As the slopes got shallower and shallower, we notice that a concave down shape is formed because I start more steeply and eventually get shallower and shallower. However, if my slope is going to increase, that is going to create concave up because I start shallow, and as I build to a steeper slope, I'm going to be concave opening upward. And in fact, this is how we define the shape concave up and concave down. So we'll go ahead and define that in a minute there, but we've really just discovered what is meant precisely by something that's concave up and what is meant precisely by something that's concave down. Let's go ahead and take the derivative now. So the derivative can be found easily using the power rule, which is 3x squared. All right, so notice that this function itself, this derivative itself, actually is changing, has its own rate of change, which is what we noticed, right? That the slope itself is going to be changing. And the derivative, of course, represents the slope. So we can take the derivative of the derivative, which is known as the second derivative. So what I'll do is I'll take the second derivative, which just means that I'm taking another derivative. So I'm going to use a second prime notation here. And here I'm taking the derivative of this function. So the second derivative is the derivative of the first derivative. Well, the derivative of this function is 6x. And this is quite remarkable, because what we've seen is that the relationship between the first derivative and the original function is the exact same as the relationship between the first derivative and the second derivative. Right? The second derivative is telling you the rate at which the first derivative is changing. Or since the first derivative just represents the slope of our original function, the second derivative tells us the rate at which the slope is changing, which we can see here, right? We noticed that the slope itself was actually changing in a certain way, and this is described by the second derivative. So we can then use the second derivative to tell us whether something is going to be concave up, whether a function will look concave up or concave down, by looking at the second derivative. Because if the second derivative is positive, right, that means that my slope will be increasing, right? This tells me the rate of change of the slope. So if my second derivative is positive, like it is to the right here from 0 to positive infinity, we know that we're going to have a concave up looking function, because this tells us that the slope is changing in a positive way. However, if our second derivative is negative, as it is here to the left, we know that we're going to have concave down, because if something is decreasing, right, if the slope is decreasing, in other words, its rate of change is negative, that means that we're going to have a concave down shape. All right, so let's go ahead and formalize this a little bit more. So here is the definition of concavity. So the graph of a differentiable function, y equals f of x, is concave up, we just saw this example, concave up on an interval if the derivative is increasing on that interval. That was that green section that we worked with in the discovery problem. And it will be concave down on an interval if the derivative is decreasing on that interval. So we saw that interval where we looked at those red tangent lines from negative infinity to 0. We saw that the slope was decreasing. In other words, the derivative was decreasing on that interval, and so it was concave down. So here again is our example of the cubic polynomial x cubed. And we have concave up here because the derivative, y prime, is increasing. And concave down over here from negative infinity to 0 because the derivative decreases. So the derivative y prime increases from 0 to positive infinity and decreases from negative infinity to 0. And so here we have concave down, and here we have concave up. And at this point, we now want to determine a test, or a way in which we can figure out whether a function is concave up or concave down on a certain interval. So that's going to require us to look at the way in which the derivative changes. And so that will lead us to the second derivative. So let's go ahead and really clearly define the relationships again between a function, its derivative, and then also its second derivative, and we'll use that to come up with a test for concavity. So in order for us to understand and apply the concavity test, it's going to require us to clearly understand the relationship between a function, its derivative, and its second derivative. So I've created a little sort of layering system to help put our thoughts in order. Given a function f of x, the original function, f of x, is just the y value of that particular function, or the distance from the x-axis. If I take the derivative of this function, f prime of x, the way we've defined it is to be the instantaneous rate of change, or the slope, of my original function at any point. And the reason that is, if you remember many ages ago, we defined the derivative as the limit, as x approaches h, of f of x plus h minus f of x over h. In other words, we defined it to be the slope at an instant, right? We took the average rate of change and we narrowed it down until we were literally at that instantaneous point. And that is our instantaneous rate of change, or the slope. Now, the derivative tells me something very interesting about my function f. It tells me whether the function, my original function, is increasing or decreasing, right? Because if the slope is positive, so if the derivative, if f prime is positive, then my function will be increasing. It has a positive slope. If f prime is negative, then it has a negative slope, so it is decreasing. My original function is decreasing. This leads us to the second derivative. So the second derivative is just the derivative of the first derivative. And so the relationship is the same as the relationship between the original function and its first derivative. When I take the derivative of a function, what I'm doing is I'm finding the instantaneous rate of change. So when I take the derivative of the first derivative, I am finding the instantaneous rate of change, or the slope, of the first derivative. And that is exactly what the second derivative is. There's no new rules required. I'm simply applying the derivative again, which will give me the instantaneous rate of change of f prime. And so the relationship is the same. That means that the second derivative tells me if f prime of x is increasing or decreasing. In other words, if f double prime, the second derivative, is positive, well, that means that the slope of my derivative is positive, so my derivative is increasing. And if f double prime is negative, well, that tells me the slope of my derivative is negative, and so my derivative, f prime, is decreasing. Well, guess what? The definition of concavity is whether or not the derivative is increasing or decreasing. So f double prime of x, the second derivative, actually tells me the concavity of my original function. So it's very important. So going back over once more, the original function is just the y value of that original function, or the distance from the x-axis. The derivative of my original function tells me if that original function is increasing or decreasing. The second derivative, which is the slope of the first derivative, tells me whether my original function is concave up, which will be the case if the second derivative is positive, meaning the slope is increasing, concave up, or concave down if the second derivative is negative, because that would mean that my first derivative is decreasing, and so my original function will be concave down. All right, with this in mind, we've literally just said the concavity test, right? How could I test if something is concave up or concave down? Well, I need to know whether the second derivative is positive or negative. If it's positive on that interval, then I'm going to have concave up. If the second derivative is negative, then it's going to be concave down. And this leads us to the concavity test. The graph of a twice differentiable function, y equals f of x, is concave up on any interval where the second derivative, f double prime of x, is greater than 0, and concave down on any interval where the second derivative is less than 0. Notice that it's twice differentiable. This function has to be able to take the derivative of this function twice, right, so that I can get the second derivative. And then using the second derivative, I can test whether it's concave up or concave down. All right, so now we have not only a way of testing whether a function is increasing or decreasing, but we also have a way of testing whether a function is concave up or concave down. In other words, how is it increasing or how is it decreasing, right? And this is going to be very helpful because it just tells us another layer of information about our function. So let's go ahead and find the concavity of a couple of functions. All right, so we have a couple of functions here, and we want to determine the concavity. So we're going to use the concavity test. Now, the concavity test says that on any interval where the second derivative is positive, it's concave up, and at any interval where the second derivative is negative, it's concave down. Well, this is screaming sign chart for the second derivative so that we can parcel it up into intervals and figure out whether it's positive or negative on each interval. All right. So to make a sign chart for the second derivative, I've got to find the first derivative and then take the derivative of that to get the second derivative. So let's go ahead and find the first derivative. So the first derivative is going to be 2x. And then the second derivative is just the derivative of the first. Well, the derivative of 2x is going to be, again using the power rule, 2. Now, this is a very simple situation, and you can already tell what the sign of the second derivative is going to be, but we want to make a sign chart just to help us prepare. So if I'm going to make a sign chart for my second derivative, label what it is. It's going to be a second derivative. Remember, I want to find any place on the interval, and this is for all real numbers, where my second derivative is not going to have a sign, meaning it's either going to be 0 or undefined, right? Critical points of the second derivative. So where will this be 0? Well, nowhere, right? Where will it be undefined? Well, nowhere. So I'm actually dealing with every possible value, so I just have to plug in any value I want and see what the sign is. Well, clearly the sign is going to be positive, all right? So it's going to be positive everywhere. The second derivative is always positive. Now, I want to get in the habit of, underneath each interval, writing what this particular piece of information tells me about my original function. So going back to those layers that I described, remember, the second derivative tells me the concavity of the original function. And when the second derivative is positive, our concavity test, second derivative is greater than 0, that means that our function is concave up. So I'll write here that this means y is concave up. Okay? Now, of course, I could also make a first derivative sign chart to figure out where the function is increasing and where it is decreasing. If I look at the graph of this function, right, it's just a parabola, and I can see obviously that it's concave up everywhere. If I were to look at the first derivative, I would see that the first derivative is 0. The slope of this function is 0, right at 0, and that it's decreasing to the left and increasing to the right. So I'd actually have one critical point for my first derivative. All right, let's take a look at number 2. Try this one on your own, and then we'll go over it together. All right, so I've taken the first derivative here. Derivative of 3 is 0. The derivative of sine of u is cosine of u times the derivative of the inside, and the derivative of x is just 1, so I just have cosine x. But I want to determine concavity, so using the concavity test, I need the second derivative. So I'm going to take the derivative of the first derivative. So the derivative of cosine of x, well, the derivative of cosine u is negative sine of u, so negative sine of x, times the derivative of x, which is 1, and so I'm just done at y double prime equals negative sine of x. Now I want to construct my sign chart in order to determine where the function could be is concave up and where it is concave down. Try that on your own first, and then check with the sign chart that I create. All right, So I'm trying to determine the sine of y double prime, which means I'd like to split up the interval from 0 to 2 pi into sections where I know it'll have a sine. So I need to determine the critical points, which are the points that y double prime is either going to be 0 or undefined. So what will make sine of x equal to 0, that is in between 0 and 2 pi? Well, looking at my unit circle, I know that sine is 0 when the angle is 0. So sine of 0 is going to be one of them. So 0 is an input, and that makes y double prime equal to 0. Going around my unit circle and working my way to pi radians, that will be another place that will make sine 0, and so pi works as well. And I can include 2 pi, and 2 pi certainly works since 0 worked. And so 2 pi, and all of these are going to make the second derivative 0. So now I'm going to test in between what is the sine of the second derivative in between 0 and pi. I can try a value that's in between. Let's try pi over 2. So sine of pi over 2 is going to be 1, and times a negative will be negative 1. So I'll have a negative value. And in between pi and 2 pi, perhaps 3 pi over 2, and sine of 3 pi over 2 is negative 1, but times a negative will be positive, and so I'll have a positive value. Now I want to write down what this tells me about the concavity. Remember, I want to be capturing what this sign chart tells me about my original function. So if y double prime is less than 0, then y is concave down. If the second derivative is greater than 0, or positive, then y is concave up. And so there I have my answer written out. My function, 3 plus sine x, is concave, I abbreviated, concave down on the interval from 0 to pi. Notice it is the open interval. It's not concave up or down right at these points. It's only in between them. And concave up from pi to 2 pi. Let's look at this example in a little more detail, because there's actually something else that we can define, which is an important characteristic of a function. So here I've graphed y equals sine of x plus 3, or 3 plus sine of x. I can tell it's translated up 3 units. And then I've also graphed the second derivative, negative sine of x. So a couple things to note. Between 0 and pi, my original function is concave down, right? What does that mean? Well, that means the slope of the function is decreasing, and that makes sense, right? Here it's positive, it's still positive, but it's getting smaller, still positive, getting smaller, still positive, getting smaller. Here it's 0, and it's still decreasing. Right now it goes negative, goes negative, goes negative. Then there's a point where all of a sudden we switch from concave down, meaning the slope was decreasing, to a place where we're concave up, meaning the slope is increasing, right? So all of a sudden, the slope was negative, and now it's starting to get a little less negative, little less negative, little less negative. It's increasing, it's increasing, it's increasing. It's 0 now, it's still increasing, and it's on its way up. It's moving positively, and that's why it's concave up. Well, this is obviously a big switch, right? Whenever you're going from the slope decreasing to the slope increasing, that's going to be an important thing to track. And we call the point where that happens a point of inflection. And so notice what's happening at this point. The second derivative was negative. That meant that the slope was decreasing, right? And so that's why we had something concave down. Well, when the second derivative switches to being positive, that means that we're going to switch from the slope decreasing to the slope increasing. In other words, we're going to switch from concave up to concave down. And that is going to occur when we switch the sign of the second derivative. So either going, as we do here, from a second derivative which is negative to a second derivative which was positive, or if it were the other way around, this point is where the concavity changes, which is called a point of inflection. And those are points that we're going to want to track. In fact, I very vividly remember on my AP Calculus exam, one of the questions asked very specifically for where a function was concave up and down, and to list any points of inflection. So it will definitely show up. So let's go ahead and define that clearly and make sure we can find points of inflection. here's the definition for a point of inflection. There are two criteria actually, and one of them is obviously the one we just talked about, that the concavity must change. So a point where the graph of a function has a tangent line and where the concavity changes. So has a tangent line just means that it has a derivative at that point, right? And the concavity changes, that's the big one. Well, the concavity is determined by the second derivative and the sign of the second derivative. So if the concavity is changing, that means the second derivative changes sign. And of course what this means is that the points of inflection are going to occur at points where the second derivative is either equal to 0 or undefined, because that's where we'll be able to switch from either positive to negative or negative to positive. Let's use the example that we just did to kind of illustrate this point again. So here's the example that we just worked on, and oftentimes you'll be asked, where is the function concave up, concave down, and what are the points of inflection? So here I'm looking for where the second derivative changes sign. Again, my second derivative sign chart is going to give me this information. I can see that the second derivative switches sign at pi. I can clearly see that illustrated in my graph, and that represents a point of inflection. So what I would say is x equal pi is a point of inflection. At this point, we're ready to tackle the second derivative test for local extrema. It's sort of an extension of the first derivative test and can be used in lieu of the first derivative test when it is more convenient. So let's go ahead and take a look at that now. All right, so let's look at this second derivative test for local extrema. Before I talk about this, it's very important to know this. This is not an add-on to the first derivative test. The first derivative test does a perfectly wonderful job of locating local extrema. This is just another test that is sometimes more efficient. Sometimes it's not. Sometimes it's way harder, but sometimes more efficient, and it's just another way to identify local extrema. And it takes advantage of the information that the second derivative tells us. Okay, so here's how it goes. Option 1, if the derivative at some point c is equal to 0, right, so we have a critical point, derivative is equal to 0, the slope of my function f is 0, and the second derivative at that point is less than 0, then f has a local maximum at x equals c. Second option, if the slope at c, the derivative at c is equal to 0, and the second derivative at c is greater than 0, then f has a local minimum at x equals c. Now, let's illustrate this by looking at it graphically. So let's say that we have some point at c1, and it satisfies criteria 1. So that means that the slope at this point, the instantaneous rate of change, is 0. So this point here has an instantaneous rate of change of 0, meaning it can't be a part of the curve where the slope is anything but 0. So it has to be a perfectly flat point. Now, in conjunction with this second piece, which is that the second derivative at this point is less than 0. Well, what does that mean? We just talked about how the second derivative determines concavity. So here, if it's less than 0, then we know that the function is concave down. All right, well, let's put these two facts together. We have this point where the function has a slope of 0 and the function is concave down. So it can't look like this, that would be concave up. It has to look like this, concave down. And this point here has to be where the slope is 0, the derivative is 0. So it can't be like this. This has to be that kind of apex point, that maximum point. In other words, this has to be a local maximum. All right, so those two criteria make sure this is a local maximum. All right, well, let's consider the second option. Let's say you have some point. Again, the slope is 0 at this point, and the second derivative is greater than 0, meaning that it's concave up. The function is concave up. Well, it can't be concave down. It has to be concave up, and this point has a slope of 0, so it can't, the curve can't look like this. It has to look just like this. And so this will be a local minimum. Okay? So I don't know how it would join, but you get the idea. The point is that if both of these conditions are met, then this point is certainly a local minimum, and if both conditions for one are met, then it has to be a local maximum. Now, the reason we might want to use this test is that look at what we have to determine. All we have to determine are where the derivative is 0, and then find the value of the second derivative at that point. So we don't actually have to find the value of the first derivative on all those intervals. We would just have to find what makes the derivative equal to 0, and then we could use the second derivative to test out whether it will be a local max or a local min. So let's try one quickly, and then you can get on to the homework. Let's use the second derivative test then to find the local extrema of this function. So I know that if I'm going to use the second derivative test, I'm finding the first derivative, finding the point C that makes it equal to 0, or points, and then testing whether the second derivative is greater than, or excuse me, less than or greater than 0 at that particular point C, and using that to determine the type of local extrema. So let's find the first two derivatives and use those to conduct our test. So the first derivative is 3x squared minus 12. Taking the second derivative will be the derivative of the first derivative. And when I differentiate 3x squared, I'm going to get 6x, and derivative of negative 12 is 0. So I have my two derivatives, and now to conduct the test, I need to find where the first derivative is equal to 0. I can factor this first derivative to 3 times x squared minus 4. So f prime equals 0 when x equals plus or minus 2. Now, those are the two values that make the derivative equal to 0. There are no endpoints, and there are no values that make it undefined, so these are the only two that I have to check, and I can use the second derivative to do that check. I'm going to plug these values into my second derivative and use that to determine the type of local extrema. So f double prime of 2 is going to be 12, and f double prime of negative 2 is negative 12. So looking at the first one, when I plug this critical point of 2 into my second derivative, I get that the second derivative is greater than 0. So this is a local minimum. So we have a local min at the point 2, 12. When I plug in my critical point of negative 2, my second derivative is negative. So we have a local maximum at negative 2, negative 12. So that is how we use the second derivative test to determine local extrema. Now there's one last thing that is important, and that is noticing that the second derivative test only works if you can take the second derivative. Sometimes it's really hard to take the second derivative, so you just use the first derivative test instead. But also that if the second derivative is equal to 0, notice neither of these situations include it being equal to 0 or undefined. If your second derivative is equal to 0 or undefined at this particular c value that you found, then the second derivative test won't work, so you'll need to go to your first derivative test. But if you notice that it's easy to take the second derivative and you're comfortable with taking that derivative, then go ahead and use the second derivative test, and it can potentially be a lot less work than the first derivative test. All right, at this point you're ready to go on, so move on to the Unit 4.05 homework.